Hello, everyone. Today, our speaker is Koray Karabina from the University of Waterloo. So he's going to tell us about secure boundary matrix reduction algorithm using homomorphic encryption. Okay, thanks. Well, you can take it away, Koray.
Thank you very much for the invitation. It's a pleasure to be here. So this talk is about our recent work, trying to bring different fields together. As you can see from the title, I'm going to talk about matrix reduction algorithm for topological computations, which is a very popular tool for topological data analysis. So I'll start motivating the talk by the usage of TDA in recent years. And then in particular, I am going to talk about a secure computing tool, which is homomorphic encryption. So I'll describe this at a high level, and then I'll describe some of the challenges so that we can really relate how this homomorphic encryption can be used to compute some of the topological parts that we need, which is in particular a boundary matrix reduction algorithm as one of the main algorithms in the persistent homology computations. And once you have an idea of, I know that this is a hardcore topology group, so but I really have to say some things about the TDA and the use of maybe persistent homology a bit. So it's really hard to skip that part, but I have to keep that part light too, because I want to talk a lot about homomorphic encryption and secure computing of those algorithms in general, not just TDA computations, but maybe I'll try to give you a big picture of how to really take an algorithm and then try to compute this in its encrypted form. So in a way, I'll be providing some background on TDA, some background on homomorphic encryption, and I'll try to merge them towards the middle of the talk so that we can get a very concrete picture of the secure matrix reduction algorithm. So in particular, I'll describe some of those challenges, and then I'll describe a version which address those challenges, and then I'll talk about our implementation. And then this is initial, I think, really recent work, and there isn't really much, previous work on this. So there's a lot of low-hanging fruit in the field and a lot of fun problems to work with from my perspective. So I'll talk about some of maybe future research directions so that could be of interest to, I think, anybody either in topology field or in cryptography or even like algorithmically. They are very interesting in my opinion. Okay, so here is something that I think you know very, very well. So we talk about topological features. Again, excuse me if this is really a very light touch, which I'll try to get a bit more involved. But what we try to do in any data analysis work or machine learning, let's say, we try to extract features from the given data. So the pipeline is really very complicated in general. Most of the time you start with data, which we call point cloud. In TDA, I think it's very common to call it point cloud. And then from this data, you use different techniques to extract features. And if those features could be, of course, like fixed length features, variable length features, could be integers or real vectors. And then the hope is those features are useful to begin with. And sometimes those features are used to measure the similarity of two data points maybe, and then you can use clustering algorithms or predictive analysis. You can run those things on. And sometimes those feature vectors are fed into another pipeline for machine learning, and then you try to learn more from those features. So in the case of, I think, topological features, it makes sense to talk about those Betty numbers. And then visually they correspond to connected components, loops or voids of the given data. And maybe at least up to, I think, 3-dimensional, we can visualize those things. And again, in this example, if you look at the feature vector as the triple of those Betty numbers, first 3 Betty numbers, you can now directly measure if two data points are similar or not. In this case, they are really similarity of the equivalence for topological being topological objects. So what TDA can already do is it can encode and extract features. It can encode the data in a really smart way, and then it can extract features from it. And then those features are useful to measure similarity between two feature vectors. And then one very popular method is the bottleneck distance, as you know. So you can really get the persistent diagrams, and from those persistent diagrams, you can run the bottleneck distance algorithm, which now gives you a sense of similarity of two data sets, maybe. And then this, there are lots of interesting features, of course, this method, because it is tolerant to noise. So small distortions in the data set is not going to affect the similarity measure, and or maybe some of the linear transformations is not going to affect it at all, because we look at some geometric features too. So there's a lot of, I think, attractive features that TDA provide, whereas we don't really get from other machine learning algorithms or feature extraction algorithms to begin with. So there are really a lot of advantages compared to other methods that we know. And then there are, of course, disadvantages, but then I see this as a complementary tool. So it makes sense really to investigate on this topic quite a lot. And then we've seen a lot of examples that TDA can show something about your data, whereas other methods cannot. Either more accuracy or more efficiency you get out of it. And then what we want to look at, and what I am going to talk about in this presentation, is this is such a great cool tool, and given data set, you can really learn some features and then measure similarities. But now the question is, doing this, I almost most of the time have to violate the privacy of my data, because what I do is I hand my data to a service provider. They run their algorithms on the data set, and then they tell me the result. And this means they really, at some point, either in the training of during the training of their algorithms, or evaluating their maybe trained algorithms, they have to look at my data. So the point here is really to still utilize machine learning tools, data analysis tools, in this case TDA, or in general computations that we do for TDA, and you would like to evaluate those algorithms on encrypted data. So that's really the distinction that I'm going to be looking at the algorithms that we already know, and then we'll try to see if those algorithms can be computed on encrypted data without decrypting it at all. So I assume the audience is not very familiar with homomorphic encryption or in general encryption. So I would really prefer, like, if anything is not clear in the beginning, you ask me, and then I can clarify early in the beginning, because later in the talk, we'll be going back to those primitives and the, I think, restrictions or the constraints that I would like to introduce. So this is I think, typical toy example that there are, I'm copying the same toy examples from the previous slide to motivate the, I think, why topological features are important. As I already discussed in the setting, you would like to think of this as a multi-party setting most of the time for cryptographic computations, because there's a set of parties who own their data, and then there's a party who, what we call the cloud service providers, who have those intellectual algorithms and the computing power and can compute on the data. So in this case, let's say they came up with a great feature extraction algorithm which can indicate the existence of a cancer cell or not. And then, of course, users which are potential patients or patients themselves would like to use this service to query whether they have cancer or not. So pretty much in this toy version of this application, I would send my three-dimensional feature vector to the cloud, and they would make an equality check, which is one of the computations that we'll have to do in homomorphic encryption. And then I get the result yes or no, right? So if they're equal, then it's a yes. If they're not equal, it's a no. But of course, this is a super simplified version, because in general, equality check is very, very limited. You have to look at distances with respect to some thresholds or radius, and then feature vectors are not as easy as it looks in this slide. But again, this violates your privacy extremely, because even you encrypt your data and send it to cloud, the cloud will have to decrypt it to really run the equality check. So you like to avoid this case. So in a way, we would like cloud to run computations for us, but never learn our data and never learn the result. So the only thing that they have to do, compute, send it to us, and as the users of the data, owners of the data, we would like to avoid computations, but we would like to be the only ones who know about the result. So that's really the constraint, what we call confidential computing or secure computing or encrypted computing. So here is how it is supposed to look like. It is almost the same picture, but except you can think of this as now encrypting everything, putting it in a box, and this data will never leave the box, and nobody can really unlock the box except the patients in this example, or the owners of the data. So everything is in the box. So if you look at this picture, the cloud will magically run some computations, and then they're going to still compare if their tumor marker feature vector is somewhat existing in my own data set, but then everything happens in the lockbox, and they cannot unlock the box. So they run the computation for us, but they don't know the result. They can never learn my data either, because I also shipped it in a lockbox. So again, the constraints are patients are able to encrypt their data. Cloud service provider or third parties can encrypt the data under other users' public keys. They cannot decrypt, so they can never unlock the box. And so the only way that they have to be useful in this picture is that they have to compute on encrypted data. And then patients are more capable. They can decrypt the data and then learn the result. So, and then, of course, there's a competing case now. Patients would like to provide the security and confidentiality and privacy of their data, and same as for cloud service providers, because they are providing this service, so they do not like to reveal their maybe feature vectors. So as much as the patients are trying to provide their privacy, protect their privacy, cloud service provider is also trying to protect their privacy, so they do not want to reveal M0 in this case. So M0 could be really the intellectual property that they're holding on. Okay, so maybe I'll pause here. Is there any question in terms of the, I think, abstract motivation of the secure computing or confidential computing? Or is everything good to go?
Can you tell us more about how this M0 equals M1 box will do it? Because yes, they don't have to be encrypted in the same way, right? They could be
M0 and M1 will be encrypted in the same way.
The tumor center, say, could be encrypting in their own way, and you could be encrypting your own way. So how do they decide they're equal? M0 equals M1?
That's a very good question, and that's
knowing each other's encryption methods.
Yes, I'll explain this in detail, but just to be clear, M0 and M1 will be encrypted using the same key. So they'll be using the same algorithm to encrypt, but M0 for patient 1 versus patient 2 will be encrypted in 2 different keys. So when I'm interacting in this application, M0, when I'm talking to patient 1, it is going to be encrypted under their public key, their encryption algorithm. But when I talk to patient 2, I'm going to be encrypting the same data using a different public key. But that's consistent in a box. So those 2 boxes are consistent, or like triple boxes are consistent in their own way. To be more clear, maybe I am going to be referring to a public key encryption scheme, again in an abstract way. So any public encryption scheme will come with a triple of algorithms. There's going to be a key generation algorithm, there's going to be an encryption algorithm, and there's going to be a decryption algorithm. And the messages are supposed to be secret messages, because we are trying to protect the security and privacy of those data sets. And then ciphertexts are encrypted messages, so I can really assume that they're public, because I'm going to assume that this encryption algorithm is a strong encryption algorithm that nobody can decrypt. So after you encrypt your message, it's good to go. You can put it in the public, you can send it to cloud, and you don't really worry about it because you're the only one who can decrypt it. So key generation algorithm and encryption algorithm are randomized algorithm, they're probabilistic. So what this means is if you run the key generation algorithm, you get a pair of public key and secret key, a pair of two keys, a pair of keys, and a public key, as it sounds, is public information, so I can really let everybody know about my public key. But secret key, I hold on to it, so I am the only one who knows the secret key as the generator of this key pair. An encryption algorithm takes input the public key in the algorithm. That's why everybody can encrypt under my public key. So as the patient number one, once I have my public key from this key generation algorithm, I can release it to the public, to the whole world, and then everybody can start using my public key to encrypt messages for me. So in the previous slide, the cloud would get public key from patient one, public key from patient two, and they can encrypt their secret message, which is the indicator of the cancer cell, maybe under under the same algorithm, but with different public keys. So the important thing is that encryption algorithm is also probabilistic, meaning that if you encrypt the same message 2 different times using the same public key, you still get different ciphertexts. So that's why it's a randomized algorithm. You cannot really distinguish it. So what we assume is for the security of this encryption algorithm that the function behaves like a random function. So for a fixed public key, you should not be really able to distinguish the output of this encryption algorithm from randomly distributed strings of the same length. Okay, so in the whole, I think the rest of this talk, or at least in this slide, I'm going to be referring red as the secret information and blue as the public information. So in our case, all those MIs are private information. Patient and patient two generates their own public key, secret key pairs, and then they encrypt their data under their own public keys, and then they ship this to the cloud. So now the cloud has the public key of each user in the system. They can encrypt their own data using public key 1, public key 2. So they get different ciphertexts, 2 ciphertexts. And then what they can do, which we will discuss, they can also run those equality operators on encrypted data. So let's take it for now as a black box algorithm, but I'll explain the details. But what is surprising here is that you can get 2 ciphertexts encrypted under the same public key as one of the users in the system, and then you can check the equality of the corresponding plain text by only running computations on the ciphertext. So you get the result, you never learn the result, but the result still becomes encrypted. So what happens is that's why what we call this a homomorphic encryption scheme. It really preserves the operations. It preserves the operation, but you can really compute those things under the new world, which is everything encrypted. So you really pretend like you're doing everything as you would do in a plain text space, but now everything is happening on the ciphertext space. So you're really transferring the capability of those computations over ciphertext, and it's a meaningful operation because once you decrypt, you really get the results as if you would do them in the plain text space. But the point over here is that as computing this RI bar that I show, now I can send this freely in the cloud, in the internet, and then once each user gets their own piece, R1 bar or R2 bar, they have the secret key. They can decrypt and get their results, either they have cancer or not. So that's a generic picture of the homomorphic or in general secure computing. So you really would like those tools that allow you to at least compute basic operations on encrypted data. Okay, and here's a bit more detail. Of course, like this is sounding a bit magical. And for those, like you have to really start with some primitive before you can really extend this capability to like complicated functions. So what is given to us is that we can assume that we have a public key homomorphic encryption scheme. So the now I'm not really going to refer to the key generation algorithm, but we have a pair of encryption decryption algorithms, and then we have a pair of operations which are sort of really addition and multiplication operations. And that's the homomorphic part of this encryption scheme. So what it tells us is that if you encrypt 2 messages under the same public key. You encrypt them. M1 goes to C1, M2 goes to C2. Now you can run those ciphertext operations, ciphertext addition and ciphertext multiplication, which if you decrypt, you get the plaintext version of those operations. So that's really the homomorphic property. If maybe it's better if you apply encryption algorithm to both sides of this equation, because then you get ciphertext 1 plus ciphertext 2 is equal to encryption of M1 plus encryption M2. So that's the homomorphic property. And we do have those efficient schemes that can compute, that can realize those constraints. So we do have several public key homomorphic encryption algorithms that can have their addition and multiplication operations with some limitations, of course, that I'll refer later. But for now, like we can assume that we have additively homomorphic and multiplicatively homomorphic encryption algorithm. So now we call those like addition or multiplication operations. Now the question is, well, given those primitives to add and to multiply ciphertext, which makes sense because once you decrypt, you get the plaintext counterparts in those operations. How do I really compute other operations? Because doing addition and multiplication is limited, even though it is very useful in practice. For the previous example that you want to check the equality of two vectors or two numbers, how do you really do this? Like can I realize is equal operator on encrypted data? And then maybe like many other things we can ask, like can I invert numbers? And those numbers, you can think of it as like integers or real numbers, or integers modulo some small prime. Can I compute the square root of numbers? If you give me two numbers, can I find the maximum or minimum of those two numbers? If you give me an index, which sort of I'm trying to make my way towards like what is most useful for my purposes. But if you give me an index of numbers, can I find the maximum of those numbers, or can I find the index at which the maximum number resides? Can I compare two numbers? Like if you give me two numbers, can I conclude that those numbers A is greater than B or vice versa? And then maybe the last step which is finding the log of a vector, which is the index at which the last non-zero number happens in the vector, which is a like subroutine that we use a lot in the boundary matrix reduction algorithm. I have to say a few things over here, because when we do cryptographic computations, most of the time you work with integers or discrete numbers, but it is also very common for those machine learning applications, or in general real-life applications, you have to work with real numbers. But working with a real number is still like limited, because you have to fix the digits that we keep track of the accuracy. So in this example, for example, I only care about 2 digits of accuracy. So when I say I would like to invert a number, I only really care if I'm good in the 2-digit accuracy. So if I'm really taking the square root of a number, again, like 2 digits. So this is sort of a limitation in any computation anyway. So you cannot really have arbitrary lengths, but especially in cryptography, you have to fix it in advance. So in that sense, if I'm asking for the operation is 3 equal to 5 in their encrypted form, I should expect something telling me the 0, so that it tells me 0 means no, they're not equal. But if I'm really asking if 3.001 equal to 3.002, then by design, by definition, I do expect an affirmation on this equality, even though those numbers are not equal. Once I fix my accuracy, the algorithm is going to tell me something close to 1. And this is an approximation. So I don't really necessarily get exactly the same answer that I expect in the plaintext computation, but I get something close to the expected answer. So there are really two reasons for errors in this case, which is very important in analysis, which makes also the papers a lot longer than they would be, is that you have an error which is intrinsic from your setting of fixing the accuracy on the digits. And then there's also errors that happen in the computation, which only could be explained if you go into the details of homomorphic encryption algorithms. So same-wise, yes.
Sorry, I have a question before maybe you move on. The direct sum and the tensor up there, they're not necessarily the direct sum and the tensor of mod 2 vector spaces. Is that correct?
No, this is just an operation that we need to define. So there's a ciphertext addition, ciphertext multiplication operations. Again, this has to be sort of at the abstract level right now. But what happens is that whenever we define our encryption algorithm, it maps a space to another space. For example, a very common space is that we look at polynomials modulo quotient ring of polynomials with coefficients coming from ZP, for example. So now your ciphertext become just some elements in some algebra that you define. And then those addition operations are sophisticated operations that we define that correspond to the addition of ciphertext. So really the whole point is to design those operations so that when you decrypt it, you get the addition of the plain text or multiplication of them. It has really nothing to do with any operation that we know of naturally, but these are ciphertext operations that are defined. And that's been sort of the breakthrough results in mapping those homomorphic encryption algorithms, that those operations can be defined that respect those operations. But on the right-hand side, additions and multiplications are really addition of integers, real numbers, you can think of it as. Or in the worst case, these are additions or multiplications modulo p. So right-hand side are really our traditional operations. And the law operation here is like, I'll go back. Is there any other question on the approximated computation of those operators?
Do you have a typo on the max35 or there is another story behind that?
Max, yes, I have a typo.
Okay.
Thank you.
Just in case there's something we don't understand.
That's an error. It should be 5, yes. So the error shouldn't be that big.
Yeah, thank you.
Yeah, okay, thank you. I have to fix it. So there's even another challenge now. So let's say you are able to compute all those functions operators. Now you also have a difficulty in programming some of those algorithms that you have. For example, like I'll again refer back to this, branch outs in your algorithm, conditional statements. Like most of the time you do check the correctness of or value or the equality of two numbers right now, which happen a lot in the boundary matrix reduction algorithm, right? You check if two values are equal, and accordingly, you do an operation, the next operation. In encrypted domain, we have no way of really branching those two cases, because that would really mean a violation in the security of the encryption algorithm. So what we need to do instead is to come up with another way of converting those conditional statements into and avoid them and really get rid of them completely, but still have the same functionality for implementation. So I'll talk about it, but let's go back to the operators that we discussed. I mean, the key idea here is that actually I revealed a lot in the first part. I said like you have a nice encryption algorithm which can respect addition and multiplication. But of course, like if you respect addition and multiplication, now you can evaluate polynomials. So the trick is that most of the time, if you need to compute a function, you try to approximate it by a polynomial, and then you compute evaluated polynomial because you know to do addition and you know how to do multiplication over the side, those approximation signs. So for example, if you like manual approximation of the inversion within a bounded interval, this works really. You get the better accuracy you can have, which you could think like maybe I can pick arbitrarily large d, but you cannot, because those homomorphic encryption algorithms that we have so far are limited in their functionality, and they can only evaluate a certain number of multiplications in a row. So addition is really easy, but multiplications are limited, so that each time you multiply ciphertext in a sequential way, you have to stop at some point for very relatively small d, and that d can range from maybe like 510 to 50 for practical implementation. So you cannot really go beyond very small d's for accuracy, for efficiency. maybe something else like max AB doesn't look like a polynomial, but there are smart ways of rewriting those functions, and these are all well known now in the crypto domain, in math too, of course. But their utilization have been, I think, interesting. I skipped how to compute square root of a number, but once you have a function that can do square roots in ciphertext, now it's easy to pick the maximum of two numbers because of the equality that shows in the slide. And then maybe a different flavor is the equality operator. Well, now suppose you have your numbers A and B, and if those numbers in the ciphertext space are nicely transformed into a modular, integers modulo a prime number, now I can subtract A and B from A, and then I can raise it to the p minus first power, and we know that A minus 1 to the power A minus B to the p minus 1 will be 1 if and only if A and B are different, right? So this result on the right-hand side has to be either 0 or 1, and it's going to be 1 if and only if A and B are equal. So there are really lots of tricks and I think cool plays using very, I think, maybe simple tricks that we know already, but they're extremely helpful to really realize those functions. One of the very interesting ones that I've seen recently that we use also in our implementation is that this limit approximation, for example. Like if you can really now look at the sequence of numbers, and then if you look at the sequence of those limits as k goes to infinity, then you're going to get the maximum index 1. The index where AI is maximum, you'll get the number 1, otherwise you'll get the number 0. So these are really easy tricks, but has been very, very useful for realizing secure computations or confidential computing, because those operations will be now pretty much like all we need for example, the secure matrix, boundary matrix reduction algorithm. The trick to get rid of, avoid those conditional statements is to pretty much interpolate, because you have two cases and you want to write a function that can achieve those two cases independent of the statement that you write. So in this case, I'm replacing these two columns, two, I think, cases. If something happens, run statement 1. If it doesn't happen, run statement 2. Now what I'm replacing here is, for example, I'm writing column 2 as column 2 plus if low 1 and low 2 are equal times column 1, right? Because it's going to be either 0 or 1, and if it's 1, I'm going to get the first part in the statement, and if it's 0, column 2 will be equal to column 2. But the point here is that as the computing server, I have no idea whether I'm going to the if or else part. I'm just doing the same computation because it's like blind now through encryption. Any question on this? Because it's really the heart of like the challenges that's going to come back to us. All good. There's a delay in the audio, so I'm just waiting a few seconds, but otherwise, like we can come back anyway. Okay, so now let's back to TDA. Again, apologies that I'm presenting those things to a audience like yours, but I think I have to do this. So we want to talk about simplicious complexes in general, and also those filtering of those complexes in the time frame, because that's like how you really get the sense of persistent diagrams or persistence of the homologies. But just to set the stage, the K simplex that we have is a set of K plus 1 points, or I'm going to show this as the tuple x0 to xk. So it's really referring to a set, but it's easier in the notation. So here are some examples. There's a point. There's nothing which is still sort of has to be put on the simplicial complex sets, especially when you talk about the chain groups. And then in general, like this is really a complete graph on a given set of points, K plus 1 points. And geometrically, it's nice to show them too. So in the case of ABC simplex, for example, I'm really referring to the triangle which is filled, meaning that all the connections are made. A face of a simplex tau of sigma is a subset where you sort of delete one of those points and then you still preserve the completeness of the graph in the corresponding set. And so here are some examples. Again, if you pick the simplex ABC, now you have 3 different faces. this corresponds to the edges AB, AC, and BC visually. And then simplicial complex will be a collection of simplices. This is a finite collection, and with two properties. One is that for every simplex that you have, the face should be also in the simplex. And if you take two simplices in this complex, the intersection should be a face, and should be a face of both of those complexes that you started with, and the face has to belong to the simplex. So on the right hand side, like there's an example which is another simplicial complex, because the intersection of them doesn't really reside as the face of neither of those simplices. Okay, so here's an example, again, a very, very toy example, because that's going to show me sort of the, I think, the features that we would like to implement later. So I'm looking at the beta number 0 and beta number 1 as the simplex progresses in the time frame. So here, like if you look at the beta number 0, which is simply counting the number of connected components in my point cloud, it starts at 1, and then you throw B into the space, you throw C in the space, the beta numbers increase because I'm increasing the number of connected components. But then you add B to the picture, the edge AB to the picture. So I'm really now creating another simplex. But creation of that simplex kills one of the components that happened before. So now my connected components drop from 3 to 2. And similarly, the addition of the edge BC will drop it from 2 to 1. And then something interesting happens. Then you add the edge AC. Now you get the loop, which counts as the contributes to the beta number 1, because now I didn't have any loop before, so it was all 0. But now there is a birth of this structure, and then it dies immediately after you color everything in the triangle that you have, which sometimes you have to do because of the filtering rules. So this is what we have in the progression of the time. Like those, you can imagine that, you know, ABC were given to you to begin with, and then you were adding connections with respect to some parameters, maybe like when pairs of points or triples are all within their like neighborhood of some epsilon, and epsilon grows as the time passes. So here are two simplicial complexes, and one thing important for the computation is the P chain group CP, which becomes the all Z2 combination of P simplices in my simplicial complex. And here are some, again, like examples, and it makes sense to really consider their isomorphs. So these are groups, and since they're sort of formal groups with Z2 coefficients, I can talk about their isomorphism to Z2 or like powers of Z2. And here are some examples. If you look at C0, C1, C2 for the simplicial complex K7, you get Z2 groups of size 2 or 8. And then there's this like mapping, which we call the boundary map, which simply takes a simplex and maps it to its boundary, meaning that you take the P+1 points, and then you delete one of them, and then you take all those possible combinations and then add them formally. So this is the way that we get to those beta numbers. So we don't really have to visualize those numbers. We can just compute them running some maybe there are different ways to compute them, but one way that we described over here is to compute the rank of the homology group, P homology group, which looks at the quotient of the kernel of the boundary map at P, and it's quotient by the image of the boundary map at P+1. And the rank of this group is going to give us the number, beta number P. So on the right-hand side, there is an example. If you apply this sequence in a row, then you always get 0. So that's why it makes sense to talk about this quotient group. But that's the definition. But this is apparently not a convenient definition for computational purposes. So you like to switch to those like efficient, and we have several ways to compute those numbers, somewhat like using linear algebra techniques. But I'll talk about this more. So that's really probably everything that I need for a setup. But from here, I'll switch to the boundary matrix reduction algorithm in plain text. But before I do that, I'll just show like some computations of those, just in case like not everybody knows topological persons homology computations by heart. And easy examples over here, just confirming that the number of components in my triangle at K6 is equal to 1, and I have one loop in there that can be sort of computed explicitly using the definition that I just presented. So simply you evaluate those maps, and then you look at the groups, and then you take their quotients, and then you look at the rank of the yielding group in the end. So rank of H0 and rank of H1 turns out to be 1, which is sort of course, like easy to see even like visually in this case. Okay, so something that makes boundary matrix reduction algorithm very popular is because it is a very efficient way of encoding the whole information that you see in this like maybe time frame. So I'm looking at the same example, but I'm looking at now like what is exactly happening as I move from left to right. So if you look at the bottom of my slide now, again, like I mentioned previously, but you add B to your point cloud set, which was only consisting of a single point A. Now the number of components increased from 1 to 2. So this is what we really call the birth of a component or a structure or a element in your homology group. And then similarly, you throw C in it, and then the simplex C, addition of simplex C gives birth to the component C. And then the component B that's been introduced at time 2 maybe is going to die when you introduce the complex AB to the picture. So that's really sort of those connections make a lot of use in when you really extract those feature vectors from your data. But then, let's mark them manually here. And then similarly, when you introduce the set BC, the HBC, that's going to kill the component that's been introduced by C itself, which was the component itself. And then the loop happens, there's a birth happening over here, then you add the HAC, and that immediately dies. It doesn't persist when you fill the triangle inside. So that's sort of a useful information, as I said, because in general, what matters for especially large data set computations, you really want to keep track of persisting components. That's what we call a persistent diagram. So some of the things that maybe are born and die quickly, you simply ignore them. They don't really contribute much to the distance computation, but you want to really keep track of those persisting components. In our case, even if you sort of iterate this more, you're going to have a single component and it's not going to disappear. And some of the components lasted a bit longer than others, which is only like by a time unit 1, but that's really two examples. But you can imagine now that there's going to be a range of components or structures that's going to be born and survive longer than others. And that's what matters for persistent diagram computations. Okay, so finally, I can introduce the boundary matrix and its reduction. So again, the idea is to capture this like series of events on a sort of rather neat mathematical way and compact way. So the boundary matrix is simply the adjacency matrix of those simplices that I have on my data cloud. So it makes more sense to really look at this matrix column-wise. So each column in their index is going to is specifying a simplex. So in my case, I have 7 non-trivial simplices from ABC to AB, BC, AC, and ABC. And for each column that you fix, the ones are going to correspond to the faces of boundaries of those simplices. So if you look at, for example, the simplex ABC, you see 3 consecutive ones. And if you trace the indices at the row vector, then you see that ABC has its faces AB, BC, and AC. So same-wise, its boundary is 0, so it's all 0 vector. B is all 0 vector as column, and C is all 0 vector. And AB has 2 ones, same as BC and AC. So this is the adjacency matrix of my simplex or simplicial complex, to be more precise. And then there's this famous algorithm, which is the boundary matrix reduction algorithm, that now captures. So you see, you execute a simple, I think, number of operations, maybe not in terms of the number, but in their nature, they're very easy operations, column-wise operations. In the end, what you get is a reduced boundary matrix. And what this matrix encodes is exactly the information that we've seen sort of sequentially. So let's say something happens, you can reduce boundary matrix to your reduced boundary matrix. And then you can look at the reduced boundary matrix and say the history of these events. So every 0 column vector is going to correspond to the birth of a component. So here I have 1, 2, 3, 4 0 column vectors. So one thing to notice is that the reduced boundary matrix is almost very similar to the original boundary matrix that I started with in this case. And the only difference is really the second last column here, which is reduced to the 0 column vector. Again, like this is a rather small matrix, so nothing much happening, but something did happen. And so I have 4 0 column vectors now, and each of those indices or the labels of those columns indicate the birth of a component or a complex. So here's A, B, C, and AC, therefore I circled them by green. And this is clear too from the picture, because each time A already gives a birth, of course, to begin with, but then the introduction of B, C, and AC, as we see from this picture, is really corresponding to those structures. They are structures that are born. And then there are some non-zero column vectors where they have their last non-zero index over there. So for the column vector AB, the last non-zero item happens in the second row over here. And this really encodes information and tells us that the AB, the introduction of the edge AB, is going to kill the component that's been introduced by B itself. So that's why B was born, but now it gets killed by the introduction of AB. And same wise, ABC is going to kill the component AC has introduced in the previous time. So that's why like this is really a cool way of sort of summarizing everything in a compact way. And you can derive a lot of information from this reduced boundary matrix. And here's the explicit algorithm that does the computation. So if you look at this computation, you really process columns in an iterative way. You go from left to right, and each time you fix a column, that column gets affected by, potentially affected by all of the preceding columns, and maybe multiple times. So that's really what it is. But as you see, from a cryptography point of view, this is not very friendly, because there's lots of conditions here, and then there's an equality check of a function, and we don't know how to compute this. And then there's a modular addition over here too, which is another challenge, because most of the time in cryptographic homomorphic encryption schemes, you have to pick your field. You say either I'm going to work over integers, or I'm going to work over real numbers, or at least not modulo prime numbers. So you have to really, it's hard to switch back and forth, and this will introduce another challenge for us. Okay, so maybe to tell a bit about the computation of this reduction algorithm. So if I go back over here, as you encode this information, you're going to fix a column at some point in your algorithm, and then check if any previous column matches that column's low value. Again, low value is the index at which the last non-zero entry happens in your column. If you compare the laws, the only matching column, matching laws come from BC and AC columns. So you really now have to add the BC column on top of AC column. So since the laws match, you XOR BC column on top of the AC column, and now the entries will switch to 1, 1, 0. But once you make this 1, 1, 0, there's still a matching low value from now another column. AB didn't affect AC before, but once BC affected AC, you have to check AB again because of this while condition. And now in the next iteration, AB is going to match AC's low value, and now it means you have to XOR AC with AB. And that's like how you get the 0 vector in AC. And after that, like there is no matching low values for each pair of vectors. So you're good to go. You can end the function. Any question on the reduction of the boundary matrix algorithm? That's all good.
Did you say these diagonal circled ones are the homologies, or?
These ones correspond to the depth of the previously born homologies. So, for example,
okay, so
in the case of AB, in the case of the AB column, so it is a non-zero column. So it will, through its low index, it is going to tell us which component it killed. So
okay.
AB killed the component B introduced by B. So in the case of ABC, for example, ABC kills the loop over here, but the loop was introduced by AC. So it really tracks back to the reason for the birth of that component or structure.
So some of the running of this program, they completely get rid of the zero columns, right? If you don't want it to spend time checking the zero columns, if they have a low compared to the lows on the right-hand side, you can erase these columns, right? ABC, for example, from the beginning. Or when AC is created, you can immediately kill. And you can still recover the fact that they are the ones who create the homology, I guess, because of the lows of the other columns.
That's a very good point. And in fact, the low is not defined, as far as I know, for the zero vectors, because you don't need it, as you say, like they don't have an effect. But when that was one of the things that really bothered us, like really for a good while, because like we cannot really, when we see a column, we are going to see it encrypted. So since this is an encryption function, we cannot distinguish whether it's the encryption of zero vector or not. So to us, any encryption of column vector is indistinguishable from a random text. So there is no way that we can check if a column is zero or not. So what we have to do is actually we have to extend the definition of the law to the zero vector and make sure that this really goes through the steps as any other vector. But we want to make sure that like those additions will be dummy additions. So there is no way, once you encrypt your columns, there is no way to sort of apply all those like steps, ad hoc steps that you would do in plain text. But that's a very good point that, you know, at least we don't know a good way of manipulating those cases.
I mean, you have even in the encryption case, you have a way to say where the low is, right? By maximum, like there is a way to tell the low is, so you can detect a zero row, even when it's encrypted.
If you detect something is zero in the encrypted domain, it means you sort of break the encryption algorithm. You don't want to be able to detect anything you don't want to detect any information about the plain text. So it's impossible. As long as the encryption algorithm is secure, you cannot do that. All you can do is you can check if it's equal to zero or not, but that's going to be encrypted. So you'll never learn the result. So you can check if A is equal to zero, but all you get is encryption of the result.
But if it's encrypted and still, could you use to get rid of those columns in the
Since it's encrypted, I cannot distinguish. So I can check A0 or not, but since the result is encrypted, I cannot branch out in my code that I cannot, because I don't know the result, except that I have to make sure that this zero plays a role in the information. So that's similar to the replacing those if branches over here. Like there is no way for me to really go branch out explicitly. All I can do is rewrite the algorithm, which is avoiding all those conditional statements. So I cannot really run conditional statements on encrypted computation. But that's sort of one of the hurdles of not having those like nice things like exploiting the sparsity of the matrix, for example. Yeah. So in a way, you sort of match the worst case complexity, and you are somewhat forced to do that. Okay, so the challenges. So here's the simple boundary matrix reduction algorithm, and the challenges is that we don't know. I mean, at least when we started this research, like we haven't really seen any function, encrypted function that computes the log of a given vector on the ciphertext domain. Another point is that like this is such a simple looking function, but it has lots of, even the single while there exists an index less than 0, if something happens to that, has to be recoded, and then you have to really get rid of all those conditional statements. And then there is another detail which I won't talk so much about it, but you know, there is a combination of real arithmetic and modular arithmetic in this code, because many of those comparison algorithms or other things, even the start with, like you start with a 0-1 matrix, which is binary, but then when you compute the law of things, you get approximations, and then we chose to work with real numbers, with a homomorphic encryption that works over real numbers, meaning that your results become encoded as real numbers. But now you have to go back to the modular addition, which sort of now you have to rewrite the modular addition using real numbers representations. So these are like, that's a sort of tiny detail compared to others. And then other things that I mentioned, like in those computations, they are always, each time you do addition, each time you do multiplication, you introduce error to the computation. So at the end of this computation, you have to really analyze the growth of the error has not been really much more than a threshold, so that you can really clean the error at the very end, then you decrypt it. So what happens in those encrypted computations is that as the cloud, you compute things, you send it to the patient in this case, they're not going to get a perfect 0 or 1. They're going to get hopefully something close to 0 or something close to 1, so they can still separate those cases. So you have to really make sure when you reduce the boundary matrix, there's not going to be a 0-1 matrix, but there's hopefully going to be a matrix where entries will be close to 0 and close to 1. And then the depth of the circuit is basically the maximum number of multiplications that you perform in a sequence in the whole run of the algorithm. It is very important for us because there's a very strict limit on the depth that we can compute efficiently for the existing schemes. So the key observation, first I'll tell about the avoiding those conditional statements. The key observation that we made is, which I think is probably clear to everybody, that if you fix any column J, and then and if you take any previous column before J in this reduction algorithm, that specific column J0 is either not going to affect your column, or it's going to affect the column at most once. Because each time, in the case that it affects your column J, the low value of the J column is going to decrease, and the low value of the J0 is never going to change because you passed it. Right? So you either don't affect it or you affect it at most once. So that's been an observation which is going to be helpful to rewrite this 3-line code. And then the other thing is to compute the law of a vector. What we did is a simple transformation that takes your binary vector to a integer or real number vector, where you can have the law of the vector if and only if you can compute the maximum index of the vector that you transformed into. And we know how to compute the maximum index, as I discussed. So then the maybe a friendly version, a pseudocode for the friendly version for this loop at least is our while loop has been now switched into replaced by 2 deterministic for loops, which is no problem at all. And then the column vector is sort of, I showed you the trick before, you can really replace those if statements by just interpolation pretty much. So that's the main sort of change that goes from BM reduced to HE friendly version of it. But the details are a bit more involved, and you'll have to invite me again to discuss those things. But there are really some important details over here. So I highlighted those stuff that you can easily relate, which is very easy to understand. So there are really 3 definite for loops, statements, iterations, and then there's an update of the column. But if you look at the details, all you have to really do is you compute the law of each column to begin with. And then during those iterations, laws will change, so you'll have to recompute them. And then the orange highlighted item over here is the compatibility, so that like this modular addition, we also got rid of it because our numbers are now real numbers. So we implemented an approximation of that modular 2 addition over the columns, which is simply, I think, the freshman's dream of a minus b squared modulo 2 is the same as a plus b. So that's sort of the trick. And then, of course, the complexity is very important to discuss. So the depth of the circuit, again, like details are sort of not so hard to read. They're very messy, but really it's a rather simple algorithm to analyze. We use induction and recursion to really come up with those depth and complexity of the computation. As you see, the cost is really large because it's cubic in n, which is sort of expected, I think, because there's also the worst case complexity. I think if the worst case is matched, I don't know, but I think n cube sort of is given those 3 nested for loops, and the worst case that can happen that every vector affects every other vector, n cube makes sense. But again, like we don't know this if other cases happen. You can slim or shave some factors in the exponent. The depth is, I haven't really described the depth, but the computing depth is a bit more involved. But I don't think it's like really important for the sake of this talk. So I think conclusion is that we can handle tiny matrices. So we implemented this algorithm for 3 by 3 matrices, and then it runs in sort of amortized sum, like less than a second. But if you really have it, like it can take like hundreds of minutes if you don't use the batch technique in homomorphic encryption. I can talk about this later, like if there's a related question. But every time you see an implementation in homomorphic encryption, you're gonna hear about batch or amortized runtime. Amortized runtime we can discuss, but again, in the best case, we can for now implement 3 by 3 reduction algorithm on less than a second for cryptographically secure parameters, which is useless, of course, right? Not very useful. We have a improved method which can exceed this bound a bit, but that's like still a preliminary work. So what this means is there's lots of, I think, low-hanging fruit, and so I think there's lots of room for better encoding and filtering techniques, and also relaxed bounds and parameters. So those bounds that we drive for implementation are guaranteeing the correctness of the algorithm when it's in its output. However, these are very conservative bounds, and many of the worst cases that we assume do not happen in practice. So, but we don't know like what's the distribution of those average cases or best cases. But in general, like if you really sort of relax those parameters experimentally, we show that you can still recover the correct boundary matrix, but we have no really justifying results for those relaxations. So it will be interesting to really see, what is the real interaction between those column vectors and you do the boundary reduction algorithm. So if you do assume the worst case, this is very, I think, far from being practical for now. But also, like everything we choose is a choice. Like we designed an algorithm that can compute low. Now, if you come up with a different algorithm that can compute low, more efficient, then you're going to get a more efficient algorithm. If you have an algorithmic improvement to this structure of algorithm 6, which we have algorithm 7 in the paper, which shaves a factor n and replaces it by log n. But again, it doesn't really save you much. But I think there's lots of room for improvement. Since this is TDA talk, I would like to motivate it more for the use of this TDA in also other aspects of it. So this is a pipeline that we also posted in our paper, that you have your data, you have your boundary metrics, and then you reduce this to get persistent diagrams. And those persistent diagrams are fed into other filtering algorithms that you can get persistent images that we know how to do them. And those persistent images can be useful to be provided as input to your machine learning algorithm. The advantage is that they are more compact and they carry more information, as we believe. And then we've experimented this on the MNIST image dataset recently. And then what we show is that compared to those naive methods, if you do extract persistent images out of those digits and then encrypt the data stream and then train or evaluate your machine learning algorithm, which we use logistic regression on the encrypted data, then you get better accuracy and you get better runtime. Better accuracy was a bit surprising to us because especially achieving both was a bit surprising to us. So we expected either to get better accuracy or better runtime, and better runtime is thanks to the compact representations of TDA, but we didn't expect improvement on both aspects. And compared to those naive downscaling of images, TDA seems to be doing a lot better, or maybe marginally better, but this is an easy data set. So that's, again, the other side that I haven't really talked much about it. But there, the crypto is much more established. If you give me images in their encrypted form, I can evaluate my previously trained machine learning algorithms on them, and then that's a realistic application now. But of course, it doesn't address the securing the whole pipeline. Ideally, as the user, the owner of the data, I would like to encrypt it and hand it to the cloud, and they do everything for me, and I only get the result. So we are really looking at those parts and pieces, but so still there's room to connect those pieces. Finally, I have a set of references. The paper is publicly available on arXiv. A short version of it has been accepted to ACM CCS conference, which is in end of November, will be presented. And then the machine learning part is still undergoing, but a poster version is to appear in the Usenix poster session. And then hopefully that's going to be published soon, we're going to post it. But I think this is really initial work, a set of works, and there's lots of room for improvement, especially, that's exciting because it brings expertise from different fields, algorithmic, TDA, and crypto. So I'll end my talk here, and thank you very much for the invitation again. I did overtime a bit. I apologize for it, but I'm happy to take any questions now.
Okay, thank you, Koray. Well, we are used to overtime, so that's fine. Okay. Any questions for Koray? I have one actually. Sorry, yeah.
You go, yeah, I can do it after you.
Okay, so my question is about the efficiency. I see in this slide, it seems like it's still N-cube, or is it more than N-cube, which is the I think the normal without the HE version of the code. I think it was the algorithm which is supposed to be N-cube, right? And now it's slightly more, or is it more or less N-cube?
The complex is still N-cube. The complex is N-cube.
Okay.
Yeah.
So the encryption.
Yeah.
Yeah, the encryption doesn't really add much doesn't really reduce the efficiency much.
No, not actually. Yeah. So not on average, it increases because as Ergün referred, you can skip a lot of the things on the way. If you really do a sort of optimized version, as soon as, let's say, I'm having lots of zero vectors, I can just ignore them, and then it cuts my dimension of the or reduces the size of my matrix significantly, maybe at very early stages. But in this case, we are still processing each column with each column as if they're going to affect it. So they are really, each iteration, our complexity is constant time. So constant time means it is independent of the input. So if you run this boundary matrix reduction algorithm, most of the time you expect that things will end much less than N-cube time because of those zero columns and others that you can. But in our case, it always ends at the same time because we cannot really look into the box, and we have to make sure that every column affects every column. And most of those effects will be dummy effects. So if you look at under the hood to our algorithm, what's happening is that we are adding zero column to many other columns, or we are just doing dummy additions. For example, here by dummy addition, what I mean is if you look at the bottom right of the screen, here you want to update column 2 by column 2 plus column 1. But when the laws don't match, you just let column 2 to be column 2, like this is the relaxed part in the other part, right? But in our case, I'm still doing a ciphertext edition, which is the same cost as a non-dummy ciphertext edition. So I'm really processing each column by each column in the worst case.
Oh, okay.
And because like under the hood, like I can't really distinguish whether I'm doing a dummy edition or not.
Okay, just to make sure, so for the original algorithm, the n cube comes from the basic complexity of the Gaussian elimination, right? Is that this?
So yeah, I think this is, I mean, this is not presented as Gaussian elimination, but if you look at this version of the algorithm, I know there are other versions, but here there is an n iteration over here, right? And then here you're processing each column from left to right. So in the most extreme case, you're going to be looking at the last column. And this last column is going to be processed by the previous n-1 column. You have to check. Like by processing, what I mean is you have to do laws match, right? So you have to really talk each column preceding the last column by the last column. And once you iterate this through, some of the columns may change the law of the last column, right? And now you have to go back and check every column again. In case, like, unless you sort them and then store this information, you can skip. But if you really do it naively, that you go back and check, there's an n square many checks at most you can do, and it looks like you may have to do it anyway. I haven't really seen an example of a matrix which meets this worst case, but I think it may be possible that so that you design so that every column has to be checked n square of the time, or like n square root 2 of the time. Because it's like 1 plus 2 plus n-1. So there's about n square over 2 or big O of n squared in this while loop, and then there's n iteration of it.
Okay.
There's actually a paper by Morozov. I tried to read it nowadays with Uzay, my senior project student, and he designs an example completely works in n-cube, but the design is a little bit funny. Like there's triangles coming out of a surface of other triangles, and it's a very specific order given, and with that order you have to run it so much that it running time is actually looks like n-cube.
N-cube. So for example,
we actually nowadays working on it and try to write a program which will count the number exactly to how many processing is happening in that particular example, so that we can verify that it's actually n-cube by checking the number exact how many times it's processing it. And it should be in a few weeks we should have more specific numbers, but it seems like it's working on the worst case scenario. And the title of the paper is that this reduced algorithm worst case n-cube example. That's what the title is. I think something like that.
So for example, one interesting thing could be like if you see those nested for loops over here. Now in crypto, it's okay if things were most of the time, right? So we don't really need to run sort of like perfect accurate algorithms all the time if it is going to save you a lot of the time in the efficiency. For example, one silly thing you could try, I'm going to process this for loop. I'm going to ignore one of those for loops because I believe everything is going to be affected in sequentially, and there's a less chance of maybe going back and revisiting this k from 0 to j-1. You can really design an ad hoc version of this algorithm that you can easily save n-cube to n-square at the cost of now losing the accuracy, right? Because maybe now you're not reducing your matrix completely. However, if you can argue that on average or for certain data sets, this is not going to hurt you a lot, so that maybe if you estimate the average runtime of this algorithm, maybe that can be mapped into this like new design, which now you can say that this is not going to, maybe it's going to give you the reduced boundary matrix with probability 1 minus epsilon, right? So I don't know like how to control that epsilon, but I think it's a very useful study for crypto, because that's a huge limit on computing the boundary matrix reduction in encrypted form. So that would be, I would be very interested to see distribution of the runtime with respect to those data sets. I'm not sure like, if dimension plays a role, or certain data point clouds may give you easier time, but I don't know. So in a way, like efficiency and trade-off between efficiency and accuracy, or correctness, even not accuracy, correctness.
By the way, the Morozov's paper's titles something like persistent algorithm takes cubic time in the worst case. That's the title. And I was going to ask, is there a way to maybe avoid this loop with the K if you didn't do any operation in the previous step? Like if you don't change the law, you don't need to run it again, right?
True.
The only time you have to run it again if the law moved to up. When you're processing a column, you have a law, and then you check the things before that column. And then if there's another law at the same level, you add. So your law moves up. That's why you have to run it again. But if you didn't do anything, like if you didn't change your law because there was no other columns with the same law, then you don't have to run it again. Like so the loop with the K equals 0 to J minus 1 is only necessary if the law changes.
That's correct.
Is there any way to design it differently so that you don't have to run same column again if you didn't change the law?
I mean, the point is we also don't know if we changed the law or not in the computation.
But could you, I mean, certain like adding is done without knowing if they're equal or not by putting a sentence in it, like depending on if the laws are equal. Then
but we do those operations blindly, like when we do the new law computation over here in the algorithm, because of the security properties of the encryption algorithm, we don't know if we updated the law or not. And most of the time, like this is again like happening in the log box, like we may be doing the dummy addition of the columns, but we don't know if we did the dummy or not. If we did it, then that would not be a secure encryption algorithm. Like if there is a way to distinguish those two cases, then that would not be a secure algorithm. So it's not expected really to have this additional feature into the encryption algorithm. So it should be really blindly, like whether you do dummy addition or not, they should be indistinguishable in the runtime and the logic of it too. And also like this example, but what could happen is that like maybe you don't have to iterate this from 0 to J minus 1 each time. Like this example shows if you didn't do it at all, then you get the wrong reduction, right? Because in this example, like the second last column is updated by BC, but if I didn't go back, like I would not be able to catch this last update. So this is the K is equal to 0 part, and this is K is equal to 1 part.
Yeah, but this is only happened because the first operation changed the law. But
yes, exactly.
Certain columns, like the column before that, the law doesn't change.
Nothing has happened. Yeah, nothing has happened.
Yeah, in the previous column, the law doesn't change because there's like in the BC column, law doesn't change, but you're still running it 3 times until.
Exactly.
So is it no way to avoid that?
So what we could do, like since now I know the structure, like I can do K is equal to K from 0 to 1, for example, right? Only do it twice. If I do everything twice, for this example, I'll get exactly the same accurate algorithm, right? I'll still be wasting my time, but K from 0 to 1, like repeating it twice, will sort of address this, and maybe we'll address a large collection of matrices too. Like, so what I mean is like maybe you can do K from 0 to a small number, for each run at the cost of losing the correctness of the algorithm. Like if I do one time only here, I will be losing the correctness quite quickly, but maybe 2, 3 is enough for a large collection, dense matrices, which I don't know, like if anybody has studied it, but that's probably, I mean, that's a very interesting question. A affirmative answer would be very useful for efficiency too, because now you immediately get like n squared times a constant. But I don't know like how to really understand and relate this. I mean, I'm not sure even if it makes sense to model those matrices as random matrices. Like when you start boundary matrices, if you look at the distribution of boundary matrices, I'm not sure how their distribution looks like. I mean, I don't know of a study, like I haven't really looked into it.
These are very specific matrices coming from the boundary of a simplicial complex. So I don't know if the runtimes with arbitrary 0-1 matrices will be like related to this event.
Or looking at the density of the worst case, maybe like if you know when you generate those worst cases, like their density compared to others, I'm not sure. Like I would expect they're going to be tiny, but.
No. But a lot of reduction techniques, programs running this reduce algorithm, they have these sparse matrix methods, like to get rid of columns with zeros, things like that. They made it very fast over the iteration of the program. They've now their most recent version is RIPSAR, I think, and it's very fast because of all these reductions they found. But I don't know how many of these reductions applies in the encrypted version. Most of them won't probably. So.
Probably, I mean, I don't want to say probably not, but at least like we cannot really enjoy the conditional statements just because we cannot distinguish them from if-else counterparts. But some others may give insight, like if I know, like in general, divide and conquer techniques are very useful, but it looks like this is a process you cannot really divide and then like work independently and then bring pieces together, because even at the last step, you had to go revisit the whole algorithm. But if you process things partially, you know, I thought about it for a while, but then, you know, you can always come up with an example, at least for the cases I thought it doesn't work. But still, I'm sure like something can be done for those divide and conquer techniques.
Divide, I don't know if it's the same thing, but one other technique is to only look at the boundary between dimensions rather than the entire boundary matrix of all the simplicities, like only from 2 to 1, 3 to 2, like between the dimensions, the boundary matrix only kept on those between the dimensions. So in this case, it will be just looking at the boundary between AB, BC, AC, and vertices A, B, C, and not keep the other matrices. Like now look at the other ones. Sorry,
that's interesting. But then what do you lose?
I have a question. Isn't it possible to just, so I think it's not possible to remove the zeros before the encryption, right? Because we learn about the data in that way. So that's not allowed. Is that so? Or
you can do it in the beginning. I mean, the point is to make the sort of owner of the data compute as least as possible. But if it helps in the process, you could do those things, because like in the end, you know, the computing party, it's an easy thing to detect them, right? So if it's not heavy computation, it's not intellectual property, then they can. So if it saves things dramatically in the beginning, maybe that's a good way, but I'm not sure if there's going to be I don't know the like density of those zero columns. Like, do we expect a lot of columns in the beginning or not? Or I don't know. Or do they get introduced like for large matrices? Do they do zero vectors introduced quite a lot? I have no idea. Like, I just didn't look into the structure.
So, but in real life examples, what is the size of the matrices? Like,
I think if you don't use any, I think the basic filtration, I think the number of columns is going to be the same as the number of simplices. So if you're looking at like points of set n, then you expect to put like each, I think, n to the power d over 2, I think, is the estimate for the number of simplices, I believe, if you do the VR filtering, I think. And then it is linear in the if you use a more careful filtering, and n becomes the number of points in your data set. So easily thousands of data points, if not millions. Like TDA gets more powerful as n grows large. But linear n with small n still makes sense, because another technique that we've seen on a paper is that instead of looking at the whole data point, they subsample smaller parts and they analyze those parts, and then they recollect the information. But in general, like, I would expect maybe at this smallest, like hundreds of points, hundreds, n is 100 in this application at least.
Okay.
And cubic in hundreds is sort of a bit painful for crypto.
Okay. Any other questions for Koray? I don't know if Argen has more. He just left. Maybe did he leave? No. Okay. Any other questions? Yeah. Okay. Maybe. Okay. So maybe that's a good point to end the session. Okay. Thank you, Koray. Thank you very much for the talk. Okay.
Thank you,
Thank you very much for the invitation.